Taguchi designs are used with the goal of creating a robust product or process. Unlike other experimental designs, Taguchi designs use fewer experimental runs, are cost-effective, and improve product quality. Taguchi designs use orthogonal arrays. In an orthogonal array, each factor and the levels of each factor are weighed equally. Orthogonal arrays are mainly used to capture main effects, or how the level of each factor impacts the response, while select interaction terms can be added to determine how multiple factors work together. Significance in interaction terms can be further explored using a more comprehensive experimental design. Taguchi designs include the following factors. Control factors. These are factors that you can control in your product or process. Their levels can be set, maintained, or changed. An example of a control factor is oven temperature. Noise factors. These are factors that influence the response but are impossible to control. An example of a noise factor is humidity. And signal factors. These are factors that the user or system adjusts. An example of a signal factor is a drink dispenser machine that is programmed to adjust the volume of liquid, depending on the cup size placed under the nozzle, small, medium, or large. A dynamic Taguchi design should be used when there is a known relationship between the response and the signal factor. Signal-to-noise ratios measure how well your product or process performs compared to variability introduced by the noise factors. Higher signal-to-noise ratios are preferred and indicate less sensitivity to noise. There are 3 types of signal-to-noise ratios. Nominal is best, used to meet a target value. Smaller is better, used to minimize defects and impurities. And larger is better, used to maximize strength, yield, efficiency, or battery life. In our first scenario, let's take a look at a static Taguchi design. An engineering team is working on optimizing the process of producing biodiesel from waste cooking oil. Their goal is to maximize biodiesel yield. They identified 3 factors that impact biodiesel production: the catalyst type, sodium hydroxide and potassium hydroxide, the reaction temperature, 60 and 75 degrees Celsius, and the solvent type, methanol and ethanol. They also identified humidity as a noise factor that impacts yield. Therefore, the experiment will be done at 3 humidity levels: low, medium, and high. To begin, open the Design of Experiments app. Click on Create Design and then Taguchi Design and select a 2-level design type. Set number of factors to 3. Select an L82 to the 3 design. This notation states that the experiment has 8 runs and 3 2-level factors. Fill in the details for the factors. Click on the plus sign next to interaction and add catalyst type times temperature. Click on Alias Table to identify aliasing within the orthogonal array. A 3 appears in row 1, column 2. This means if an interaction between factor A and factor B is selected, then column 3 will be used to estimate the interaction. Click OK. The design summary sheet provides a summary of the design parameters. In row 10, columns 1, 2, and 4 from the orthogonal array are assigned to estimate the main effects. Column 3 will be used to estimate the interaction. Click on the design table sheet and enter response data under columns D, E, and F for the 3 noise factor levels. The next step is to analyze the design. Click Analyze Design. Add yield 1, yield 2, yield 3 under response. Click the plus sign next to model terms. The interaction is already included under selected terms since it was pre-specified under Create Design. Click Settings and select Larger is better since we are looking to maximize yield. Click Quantities and select all options. Click Response Summary and select all options. Click Fits and Diagnostics and select High Leverage. Click Plots and select all. Residual type is regular. Click OK. Under the node Linear Model Analysis, the signal-to-noise ratios, means, and standard deviations tables show that the interaction term is not significant. Let's rerun the analysis by removing the interaction term. Click on the green lock and select Duplicate this operation. With the duplicate, click on the green lock and select Change Parameters. Under Model Terms, remove the interaction. Click OK. Signal-to-noise ratios are used to identify the optimal factor settings that maximize yield while minimizing variability. The mean represents the average yield across different factor settings, while the standard deviation indicates how consistent and stable the process is. Let's look at the signal-to-noise ratios. we can see that two factors, catalyst type and temperature, are significant at the 5% level. This means that different levels of catalyst type and temperature will provide different values of yield. The coefficient estimates show the magnitude and direction of the effect. In the response tables, the goal is to maximize the signal-to-noise ratios and means, while minimizing the standard deviation. Let's look at the signal-to-noise ratios under the response table. These are the average responses for each factor across two different levels. The coefficient estimate for catalyst type is positive, and response at level 1 of catalyst type is greater than response at level 2. The coefficient estimates for temperature and solvent are negative, and response at level 2 of temperature and solvent is greater than the response at level 1. Delta is the absolute difference between level 1 and level 2, and rank is assigned by ordering delta values from largest to smallest. Signal-to-noise ratios are maximized under the following settings. Catalyst type is NaOH, temperature is 75, and solvent is ethanol. Similar inferences can also be made for means and the standard deviation. Let's look at the means table under linear model analysis. The p-value for solvent is 0.60182. Scroll down to the main effects plots for means. The lines for catalyst type and temperature show steep slopes, indicating a strong influence on the average yield. The slope for solvent is flatter, indicating that the different factor levels, methanol and ethanol, do not have a significant effect on the average yield. Scroll down to the residual plots for the three measures. The residual plots do not show any patterns. The next step is to determine fitted values for the three characteristics, signal-to-noise ratios, means, and standard deviation. Click on DOE Find Y from X1. Enter different levels for the three factors, catalyst type, temperature, and solvent. Values for the three characteristics will automatically populate. In our second scenario, let's take a look at the Dynamic Taguchi Design. An engineering team is interested in reducing image blur for photos taken by a drone. They identified three control factors that impact image blur: gimbal stiffness, low and high, damping algorithm, light filtering and aggressive filtering, and shutter speed, fast and slow. They also identified a signal factor, drone speed, which varies over three levels, 2, 4, and 6 meters per second. The first step is to create the design. Click Create Design, Taguchi Design, and select the following. Design type is 2-level. Number of factors is 3. Design is L82 to the 3. Fill in the factor information. Select Add Dynamic Signal Factor. Click the plus sign next to signal to add one. The levels for the signal factors are 2, 4, 6. Click on the plus sign next to interaction and add gimbal stiffness times damping algorithm. Click OK. Design Summary provides a summary of the design parameters. The number of base runs is 8. Total runs 24 is 8 base runs multiplied by the number of signal factor levels, 3. Click on Design Table and enter image blur values in column E. The next step is to analyze the design. Click Analyze Design. Add image blur under Response. Click the plus sign next to Model Terms. The interaction is already included under Selected Terms since it was pre-specified under Create Design. Click Settings. In a Dynamic Taguchi Design, the goal is to optimize the signal-to-response relationship by fitting an appropriate model. There are 3 models. The first model is through fixed point. This option is not recommended for this analysis, since it forces the fit through a predefined signal and response value. The default values for signal and response are 0, but this should not be used since image blur can still be present even when the drone is stationary. The second model is through average response at fixed signal. This anchors the average observed response at a chosen signal level. One option is to anchor the fit at a signal factor of 4, which represents the average drone speed. This option will limit the range of the response variable image blur. And the third model is without fixed point. This is the most flexible and preferred option. Both intercept and slope are estimated freely. This option is suitable for processes that have a non-zero response at 0, or when there is no clear anchor point. We'll select without a fixed point. Click Quantities and select all options. Click Response Summary and select all options. Click Fits and Diagnostics and select all options. Click Plots and select all. Residual type is regular. Click OK. Under the node linear model analysis, the signal-to-noise ratios, means, and standard deviations tables show that the interaction term is not significant. Let's rerun the analysis by removing the interaction term. Click on the green lock and select Duplicate this operation. Click on the green lock and select Change Parameters. Under Model Terms, remove the interaction. Click OK. In a Dynamic Taguchi design, the characteristic slope measures the rate of change in the response variable relative to the signal factor level. Let's look at slope under linear model analysis. We can see that all three factors, gimbal stiffness, damping algorithm, and shutter speed, are significant at the 5% level. The coefficient estimates provide the magnitude and direction of the effect. The absolute value for damping algorithm is the largest. Let's look at slope under response table. These are the average responses for each factor across two different levels. The coefficient estimate for all three factors are positive, and response at level 1 is greater than response at level 2. Delta is the absolute difference between level 1 and level 2, and rank is assigned by ordering delta values from largest to smallest. Damping algorithm has a rank of 1. Ideally, we would target slope to be 0. There should be no relationship between drone speed and image blur. Slope is closest to 0 under the following factor levels. Gimbal stiffness is high, damping algorithm is aggressive filtering, and shutter speed is slow. Keep in mind that these settings come at the cost of a lower signal-to-noise ratio and higher standard deviation. Scroll down to scatter plots with fitted lines. The scatter plots are arranged in decreasing order of signal-to-noise ratio. Response is on the y-axis, and the three levels of the signal factor are on the x-axis. Ideally, the fitted line should pass closely through the blue points.